All right, so the projector isn't working correctly, so we're making do with everybody effectively doing stuff over Zoom. So what we're going to talk about today is circuital laws. You guys on, I don't know, regular Zoom can hear me and all that kind of stuff?
Yes, we can hear you.
Awesome. All right, I apologize for the 23-minute delay in getting things started, but anyway. So the first thing that we're going to talk about today is Ohm's Law. So for Ohm's Law, it was developed by a German physicist in the late 1800s, and effectively what Ohm's discovered experimentally was that if we took a piece of material, which I'm going to refer to as a black box network, and he applied a voltage drop across the material, where I'm going to call this voltage Vs. What he did was he measured the voltage drop across the terminals, which I'm going to call V test, and the current flowing through the terminals, which I will call I test. And he found that there was a constant of proportionality between these two terms. This is exactly the experiment that you guys did at the end of class on Friday. You measured the voltage drop across your circuit element of interest, you measured the current flowing through your circuit element of interest, and then I asked you guys to find the slope. Well, the slope is related to what's called the resistance, where resistance R is simply the ratio of V test over I test. And from this, we can see that the fundamental unit of resistance is the ohm, which is defined as 1 volt per amp. Now, you may be more familiar with the expression V is equal to I times R. That's Ohm's law that you learned back in your Engineering 120 series. This is just a simple algebraic manipulation of the constant proportionality definition. Now, one thing that I want to point out here, and this is where some things can get a little bit trickier here in Circuits 1 than they did in your previous circuit analysis classes, is that signs become very, very important, okay? So with our fundamental definition here, V is equal to IR. That's true when the current is flowing into the positive polarity terminal of our material under test, okay? If the current is ever flowing into the negative polarity terminal, then we have to say that V is equal to negative I times R. So just to be clear, if I have this situation where I have a generic circuit element, actually, which has some resistance, so I'm just going to call this R sub A. I have a voltage drop VA across it. I have a current IA flowing into the positive polarity terminal. VA is equal to IA times RA. And if I have the opposite case, where I have some resistance RA, here's my voltage drop VA, and my current is flowing in the opposite direction so that it's flowing into the negative polarity terminal and out to the positive polarity terminal, then VA is equal to negative IA times RA. The reason why this has to be true is because a resistor is incapable of storing energy. Okay, so these relationships effectively force a resistor to always be absorbing power and energy. So if the current is negative, the voltage has to be negative as well, so that the product of those two things is always a positive quantity. And again, that is purely because resistors are incapable of storing energy. What are resistors used for? Anybody remember from circuits, from engineering 120, 121, et cetera? So your very, very first, or at least when I was teaching engineering 120, one of the very first things we did is we made a very simple circuit that contained an LED in series with a resistor. And then we applied a 5-volt drop across that series combination of elements to make the resistor, or excuse me, to make the LED blink. What was the purpose of the resistor in that circuit? It decreased the current going to the LED, right? So resistors are used for limiting current in circuits, okay? They do this by converting electrical energy into heat. That is the full purpose of a resistor, to convert electrical energy into heat. That's why in space heaters and things like that, there typically is a very, very long piece of wire called a coil, heater coil, usually made of a material called nichrome or something like that, that has a lot of resistance, so that when you pass current through it, it gets very hot. Typically it glows red, and then a fan is used to blow heat off of it. In your electric stovetops and things like that, the coil is nothing more than a resistor, where it has that coil shape to make the resistor very long, because this is another relationship that you guys should have learned back in your engineering, I think it was 121. Resistance R can also be determined in terms of the geometric properties of a material, right? So R is rho E, where rho E is the resistivity of a material, which is a material property, times L, the length of the material, divided by A, which is the cross-sectional area of a material. So if we have a long piece of material, it typically has a larger resistance than a short piece of material. So one thing that I'd like to do really quickly here is have you guys calculate the resistance of a piece of wire. Okay. So let's say that we have a section of wire like so, carrying a current in one end, sending it out the other. And our length is 10 meters. And this piece of wire is what's called AWG number 18, which is very similar to the wires that were used in your jumper kits in all your engineering 120 series classes. AWG number 18 wire has a diameter D of 1.024 millimeters, and the copper conductor has a resistivity of 1.68 times 10 to the negative 8 ohm meters. So if we substitute in our values, the resistance of this long piece of wire, so we're going to have rho E times L, I guess I should make this consistent. This is L over A, is going to look like 1.68 times 10 to the minus 8 ohm meters times 10 meters. My cross-sectional area is the area of my circle that has a diameter of 1.024 millimeters. So that's going to look like pi, excuse me, over 4 times 1.024 times 10 to the minus 3 meters quantity squared. And if I plug this into my calculator, I get 0.204. Let's talk about this result really quickly, okay? This 10-meter long section of wire has a resistance that's roughly 1/5 of 1 ohm. How does that compare to the resistors that you use in your engineering 120 series classes in size? Anybody remember the smallest resistor that you use in 120? Pardon? I believe it was 220 ohms. Now, it was 220 ohms when I taught the class. It might have been smaller than that since it's been a couple of years since I did it. But even if it is 10 ohms, that means that this 10-meter long section of wire is literally 50 times less resistive, or exhibits 50 times fewer resistance than that 10 ohm resistor, okay? So in your engineering 120 series, you treated all wires as having 0 resistance, and we have just explained effectively why, okay? So how does 10 meters compare to the length of wires that you've used to connect circuit elements together? It's probably much, much longer. Typically speaking, you're talking about a couple of inches in length at the most for small circuitry. So this is astronomically larger than you would ever reasonably use to connect 2 points together. And it still has a significantly lower resistance than the smallest resistors that you have experience using. So in this class, we are going to treat wires as if they have no resistance, which leads us to the concept of short circuits and open circuits, okay? So a short circuit we will treat as a simple section of wire, okay, that has a resistance of R is equal to 0 ohms. And since the resistance is 0 ohms, that means the voltage drop across it must fundamentally be 0 volts. Okay. So I will repeat myself. A short circuit or a section of wire has a resistance of 0 ohms and must have a voltage drop of 0 volts across it. An open circuit which is literally just like a break in a wire, will represent as follows. We have a piece of wire with a gap in it. Since there is a gap in the wire, the current that flows through the open circuit must be equal to 0 amps, which means we can treat this as a resistor of infinite resistance. Both of these are idealized models, okay? So let me explain what I mean by that. Let's say that we took a 1.5 volt battery, like a AA battery or something like that. And then we literally took a piece of wire and connected one portion of the wire to the positive polarity terminal of the battery and the other side of the wire to the negative polarity terminal of the battery. What would happen? get really, really hot, okay? Why does it get really, really hot? Because there's low resistance, not no resistance, okay? So a real piece of wire does have some finite resistance. We literally just calculated, okay? Well, that small resistance is passing as much current as that battery can push, or damn near it, and that's going to cause that wire to heat up. Back when I taught the Engineering 120 series, and I understand they do it a little bit differently now, but we used to have the students solder on their barrel jack connection to their battery pack about 3 weeks into the class. And before that date, we had to warn the students on a pretty much daily basis, hey, make sure you take your batteries out of your battery pack before you just put this back in your little bag. The issue being is that if the leads touched each other, they would literally melt their battery pack and the bag and all that kind of good stuff. And it happened way more than students were willing to admit. So much so that we had to literally change the project for that to no longer happen. You could also potentially start fires and all that kind of good stuff if you wanted to, but typically speaking, a AA battery really doesn't have the energy density to do that real well, but they can get very, very hot. On the other side of the spectrum, an open circuit, we say that it is impossible to pass current through it because it has the resistance of infinity ohms, but that's actually not true. It's neglecting a whole lot of physics and things like that, but I can pretty easily prove to you that it's not true. How many of you guys have ever used a hairdryer? A lot of you. How many of you ever unplugged a hairdryer while it was running and saw sparks and stuff? Some of you. That is current flowing through an open circuit, okay? It has a lot to do with electromagnetic inductance, which we'll talk about much later in this class, but effectively, most mediums have what's called a dielectric breakdown constant, which means that if you put a voltage large enough across it, current will flow. It just has to exceed a particular threshold, okay? So open circuits in this class will carry 0 amps of current. Short circuits in this class will have a voltage drop of 0 volts, but in a practical application, neither of those things are true because they're ignoring a lot of physical things that aren't particularly pertinent here. All right, so the schematic symbol for resistance, which you guys should be familiar with, is going to look something like this, where we have a series of, I don't know, triangular spikes with 2 terminals, and we denote the resistance value by its magnitude R. Resistors do not have a polarity, so it doesn't particularly matter in which way you place them in your circuit, okay? I think you guys are probably all familiar with the schematic representation. So now let's talk about the concept of conductance. So this is likely new to you all. So if resistance is a measure of a material's ability to resist the flow of current, conductance is a measure of a material's ability to help the flow of current, or effectively how easy it is for current to pass. Conductance G is simply the reciprocal of resistance R, or another way we could put it is the constant of proportionality that is defined by current divided by voltage. So the slope of the graph that you guys got at the end of your mini lab number 1, if you had current on the y-axis and voltage on the x-axis, was actually a measure of the conductance of the component that we were measuring on Friday. Okay. Now, conductance is an annoying thing. Okay, let me explain what I mean by that. Other than really this class right here, most people, even electrical engineers, won't particularly deal with conductance a whole heck of a lot until they get into their more advanced classes, having to deal with the propagation of waves along transmission lines and stuff like that. There are a couple of homework problems related to conductance, so I'm going to teach you guys a trick to handle it. Take your conductance, take the reciprocal of it to make it a resistance, and then treat it like a resistor and go on about your day. Beyond that, it is completely and utterly useless for you to know the behavior of conductance. I truly believe that as an electrical engineer. The overwhelming majority of you have no reason whatsoever to give two shits about conductance, okay? Make your life easier, convert it to resistance, and then use your resistor combination techniques that we're going to develop. Okay. All right, so let's see. Now let's talk about power relationships. So we know that power is equal to current times voltage, and we know that V is equal to I times R. Or we could say that I is equal to V times G conductance, if we so chose. So we can combine these three relationships to find that power can be expressed as the square of the voltage divided by resistance, which is the same as the square of the current flowing through the resistor multiplied by resistance, or in terms of conductance, we'll have the square of the voltage times conductance, which is the same as the square of the current divided by conductance. Okay. You guys likely were already familiar with these two. These other two, I'm just adding for completeness, but again, I actually do not expect you to ever use them. Cannot express this enough. Anytime you see a conductance, just treat it as, take the reciprocal and treat it as a resistance and move on about your day. All right, so how do we feel about the concept of resistance and Ohm's law? Hopefully this was 98% review, right? Okay, let's move along to Kirchhoffs.
Are you going to give an example of the conductance thing, of making the reciprocal and using it as a resistance?
Absolutely. So let's say that we have the following circuit element. And let's say that it has a conductance of 5 millisiemens. So here's another thing that's slightly confusing about conductances. They have the exact same schematic symbol as a resistor. Okay, so you can only tell the difference by the units. Okay, so if this conductance G is 5 millisiemens, what is the resistor that obeys the same behavior? Well, 1 over 5 times 10 to the minus 3 amps per volt. So let's see, we could multiply times 10 to the positive 3 on both sides. Sorry, let me erase this real quick. So what I'm going to do here is I'm just going to multiply by 10 to the 3 over 10 to the 3, which is just a fancy way of writing 1. So that gets rid of that. And so I have 1 over 5, which is 0.2 times 10 to the 3, or 200. And then I have 1 over amps per volts, which is the same as a volt per amp, or an ohm. So a 5 millisiemens conductance is the same as a 200 ohm resistance.
Basically, what is happening when in a conductor versus a resistor?
They're identical. It's literally just looking. So let me go back up to the very beginning here. Okay. So if we have a black box network and we observe a linear relationship between voltage and current. If we take the constant of proportionality to be voltage over current, we get resistance. If we take the constant of proportionality that relates the voltage and current to be current over voltage, we get conductance. It's literally the exact same thing. It's just the opposite relationship. They fulfill effectively the exact same role in circuits because they are the same thing, just looked at in a slightly different way. Does that make sense?
Yes.
Okay. All right. So let's look at Kirchhoffs voltage law first. All right, so Kirchhoffs voltage law states that the sum of the voltage drops around any closed path must equal to 0, or sum together to be 0. So Kirchhoffs voltage law, or excuse me, Kirchhoffs voltage law. I don't know why I wrote KCL there. My apologies. Kirchhoffs voltage law is the law of conservation of energy in circuits form. Since voltages represent a transfer of energy per unit charge, right? By definition, voltage is the amount of work or energy required to move charge from one point to another to a circuit. So Kirchhoffs voltage law represents the law of conservation of energy. Okay. So if we take a simple circuit, like so, where we have a 10-volt drop being provided by a source, and then we have a generic element A over which a 5-volt drop occurs. Then we have a generic element B over which an unknown voltage drop VB occurs, and I'm going to give it positive polarity on the right, negative polarity on the left. And then finally, we have a 3-volt drop like so. Kirchhoffs voltage law can be used in this what's called a single loop circuit to determine the unknown voltage VB. So let's talk explicitly about how we're going to do this, okay? What I am going to do is I'm going to start at the bottom left-hand corner. I am arbitrarily going to assume a direction for some current, and I'm just going to call this current I in this case. And what I'm going to do is I'm going to follow that current I from the bottom left-hand corner around this path until I reach that exact same node, okay? If my current hits the negative polarity terminal first, my voltage is going to get a negative sign. If the current hits the positive polarity terminal first, the current gets a positive sign. So for this particular example, we would see negative 10 volts plus 5 volts minus VB minus 3 volts is equal to 0. We could then rearrange and find that VB is equal to negative 10 volts plus 5 volts minus 3 volts, or negative 8 volts. That's the most simple application of Kirchhoffs voltage law. Now, yes, sir. So if I move VB to the right-hand side, it is negative. Yeah. Now, don't ever hesitate to correct me, because I'm absolutely going to make mistakes for sure. Okay. So don't ever be like, hey, Dr. Hartman, I think it's this. I'm never going to jump down your throat or anything like that, because Lord knows I make far too many mistakes. Okay. So do not feel in any way, shape, or form intimidated or not wanting to have me further explain something, because I'm going to screw stuff up. All right. So we can take Kirchhoffs voltage law as it's written here and learn something that's pretty interesting. Let's say that we have an element A and an element B. And they are connected together in parallel. If the voltage drop over element A is, let's say, 3 volts, what does the voltage drop across element B have to be? Assuming that VA and VB have the same polarity, 3 volts, right? So Kirchhoffs voltage law tells us that when elements are connected in parallel, they have to share the same voltage. That is going to prove to be an incredibly useful thing in a lot of our circuit analysis. Devaria. It'll be, that's a wonderful question, and you're absolutely correct. It'll be negative 3 volts. So if we defined the voltage VB with positive polarity on bottom, it has to have the same, so it has the same magnitude, but the opposite polarity. That means that it would absolutely have to be negative 3 volts. Wonderful question. All right, so we can also use Kirchhoffs voltage law in conjunction with Ohm's law to do a little bit more rigorous circuit analysis. So let's say that I have the following circuit. Here I have a 120 volt source. Here I have a 2Vx dependent source. I'm sorry, let me define my resistance here, 30 ohms. And let's make this guy a 15 ohm resistor, where the voltage VA is defined as such. So in this problem, we are going to use both Kirchhoffs voltage law and Ohm's law to determine the value of the current I that's flowing around the circuit in this direction. And so our goal here is to figure out I and the power supplied by our dependent source. So I'm going to put P dependent, comma, sup, to let us know we're looking for the power supplied by our dependent source. Okay. So if we start from the bottom right-hand corner, and follow our current I around its clockwise path, Michael, what's the first thing that we see? Okay, so the first thing we see is the 120 volt source. Do we see the negative polarity terminal or the positive polarity terminal first? Exactly right. The next thing we see is the 30 ohm resistor, okay? Now, the 30 ohm resistor, we are looking for the voltage drop process because Kirchhoffs Voltage Law says that we can add voltage drops together, okay? So we have to be careful here. We aren't given a polarity for the voltage drop, so we are going to arbitrarily assign one. Dylan, would you prefer the voltage drop across the 30 ohm resistor to be positive polarity on the left or positive polarity on the right? The left, okay. So I am just going to say then that we're going to have some voltage, let's call it V30, positive polarity on the left, negative polarity on the right, so that we have this quantity V30. Sorry, I have a notice I just had VX and VA here, so that's confusing. Aaron, what do I see next? Positive 2Vx. Thank you, sir. And one of my Brandons, what do I see after that? Negative Vx. Absolutely. I'm okay with that. This is equal to 0. Okay. So we could do a simplification here. Pretty easy, right? We could say that this looks like negative 120 volts plus V30 plus 1 Vx is equal to 0. Hopefully nothing too wild or crazy there. And we've got ourselves into a little bit of a pickle here, right? In as much as we have a single equation, but we have two unknown quantities. Now, in this single loop circuit, there is a common current of I that's flowing through all of the elements, right? So our goal here is to then express those two unknown voltages, V30 and Vx, in terms of that common current I. And we can do that using Ohm's law. So, Nathaniel, how do I express that voltage V30 in terms of that current I using Ohm's law? So V30 is just I 30 ohms, okay? That seems perfectly reasonable to me. Lindsay, how do I express Vx in terms of that common current I? So there's a little bit of a problem here, okay? Exactly right. Why is it negative? 100% correct. It has to be negative I times 15 ohms because the current is flowing into the negative polarity terminal of that voltage Vx. So if we substitute that in, we're going to have negative 120 volts plus 30 ohms times I minus 15 ohms times I is equal to 0, which means that we have 15 ohms times I is equal to 120 volts, and therefore I is 120 volts over 15 ohms is 8 amps. We okay with that level of algebra? Anything seem wild or crazy? All right. So we figured out the answer to our first question. Hannah, how do we figure out the answer to our second question? So we're trying to find the power supplied by our dependent source, right? So for a source, we're always going to need to know two quantities. We're going to need to know the voltage drop across the source and the current flowing through the source, right? So the voltage drop across the source here is 2 times Vx, and the current flowing through the source is just I. Now we are being asked to find the supplied power. So Hannah, is the current flowing into the positive polarity terminal of the dependent source or the negative polarity terminal? Right, it's flowing into the positive polarity terminal. Since we are trying to find the supplied power, that means that we need to include a negative sign here. Okay, because supplied power is what we get when we multiply voltage and current when the current is flowing into the negative polarity terminal. Okay, so we have our basic equation now. What I is, we know what -2 is because that's just a number, but we don't know what Vx is, except that we've already come up with a relationship, right? So we can simply substitute that relationship in. So we're going to have -2 times -I times 15 ohms times another I is going to look like -30 I squared. And dimensionally, this comes out to be -1920. All righty. How do you all feel about Kirchhoffs voltage law? Probably a little less okay than you did about Ohm's law. This one's going to take a little bit of practice because in my experience, you guys didn't get a lot of exposure to the concept of polarities and things like that in your 120 series. Michael, how can I help you? Fantastic question for which you are absolutely correct. I made a mistake there. Thank you, sir. So what Mr. Stubblefield noticed is that I have two negative signs, which means that the negative signs cancel each other out. You're 100% right. Thank you for that correction. Told you guys I was going to make mistakes. All right. Let's move along to Kirchhoffs current law. So there are actually three different formulations of Kirchhoffs current law that we'll use in this class. Okay. So what I'm going to do here is I'm going to draw a single node point, and I'm going to draw some lines going into it, like so. And I'm just going to assign some currents. Let's call this guy I1, I2, I3, I4, and I5, like so. Our first formulation for Kirchhoffs current law is probably the one that you're familiar with from your previous exposure, okay? And that says that the sum of the currents entering a node must equal the sum of the currents exiting a node. So in this case, we can see that the current I1 is entering, the current I2 is exiting, the current I3 is exiting, the current I4 is entering, and the current I5 is entering. So we would have I1 plus I4 plus I5 is equal to I2 plus I3. We all relatively okay with that. Our second formulation says the sum of the currents entering a node must be 0. So I want to be very clear about this. This does not mean I1 plus I4 plus I5 is equal to 0. What it means is that we need to look at all of the currents as if they are entering the node. Okay, and so let me explain exactly what I mean by that. So I1 is entering the node in the center. I think we're all in agreement with that. The current negative I2 is entering, since we know that we can change the direction of a current by simply applying a negative sign to its magnitude. Similarly, a current of negative I3 is entering the node. Then we have a current positive I4 is entering, and a current positive I5 is entering, and these combine together to make 0. So effectively, this is the exact same mathematical expression that we got for our KCL number 1 representation, except that we moved everything to the left-hand side of the equal sign. Our third representation is simply the opposite statement. The sum of the currents exiting a node must be 0. So a current of negative I1 leaves, a current of positive I2 leaves, a current of positive I3 leaves, a current of negative I4 leaves, and a current of negative I5 leaves, and we set all these equal to 0. This is the exact same thing as KCL number 2, except that we multiplied everything by a factor of -1, okay? Because we're looking at the currents in the opposite direction. We get to kind of choose our own adventure as to which of these 3 representation of Kirchhoffs current law we get to use at any given point in time. I would argue that for right now, since most of you are familiar with representation 1, that's probably the one that we're going to use for a bit. However, I would encourage you to get used to using representation number 3 sooner rather than later. And the reason why I say that is in just a few short class meetings, we're going to be talking about what's called nodal analysis. Nodal analysis is a very powerful circuit analysis tool in which we apply multiple instances of Kirchhoffs current law at the different nodes in the circuit in order to solve for all of our unknown quantities with a simultaneous system. And Kirchhoffs current law representation number 3 gives us the least amount of negative signs to have to deal with for simple mathematical mistakes. So again, I would argue perfectly reasonable to fall back to representation number 1 here, current flowing in equals current flowing out, because that's what you're comfortable with. But we are very rapidly going to start using representation number 3. Okay. So let's apply KCL to a circuit. So let's say that we have a 5 amp source in parallel with a 10 ohm resistor in parallel with a 1 amp source in parallel with a second 10 ohm resistor in parallel with a 6 amp source like so. And our ultimate goal here is to determine this current flowing down through this 10 ohm resistor, which I'm going to call IX. So this particular circuit is an example of what's called a single node pair circuit. In a single node pair circuit, all of the elements are connected in parallel. From Kirchhoffs voltage law, what does that mean? The same voltage drop occurs over all of the elements. So, Mr. Stubblefield, I believe it was you who answered that question. So could you tell me what polarity you would like to assume for the voltage? Positive polarity on top or positive polarity on bottom? Positive polarity on bottom. All right, so I'm just going to call this voltage V. Common to everything, I arbitrarily put it across the 10 ohm resistor on the left, but because everything is parallel, that same voltage drop V occurs across all of our elements. All right, Davis. We are going to apply Kirchhoffs current law at either the top node or the bottom node. What is your preference? The bottom node. All right. We're going to apply Kirchhoffs current law at the bottom node. So I am just going to label the bottom node real quick here. Put it in red. Now, Ashley, do you have a preference as to which formulation of Kirchhoffs current law we use? So number 1 says currents entering equals currents leaving. Number 2 says we treat all of the currents as if they're entering the node. Number 3 says we treat all of the currents as if they're exiting the node. Number 2. Okay, so number 2, we're looking at currents that are entering the node. All right, so I'm just going to write this down here real quick. KCL number 2 at bottom node. So we are treating all currents as if they are entering the node. So that means we're looking for this current, this current, this current, this current, and this current. And we're going to add them all together and set it equal to 0. Because those are the 5 currents that are entering the bottom node. So how do we express that 5 amp current supplied by the source on the left as entering the bottom node? Victoria, you have any thoughts? Negative 5 amps, absolutely correct. Kevin, how do we express the current flowing through the 10 ohm resistor on the left flowing down? So we're going to have to use Ohm's law here. Right, so it'll be V over R. I agree there. I disagree. Yeah, well, so let's talk about why I disagree. Okay, it might seem like an arbitrary decision here. That current is flowing into the negative polarity terminal and out the positive polarity terminal, right? So since it's flowing into the negative polarity terminal, our Ohm's law relationship needs to have a negative sign. That's the hard and fast rule. Excuse me. Devarier, what do I do with the 1 amp source? Leave it as is, plus 1 amp. Let's go right, we'll move along. Seth, what do I do about that second 10 ohm resistor? So, sure, we can do that, negative V over R. Alternatively, we could express that as simply the current IX. Either way works. All right. Let's see, Dustin, what do I do for the 6 amp source on the right? Negative 6 amps is equal to 0. So let's do some mathematical manipulation here. I'm going to have negative twice V over R is equal to 5 amps minus 1 amp plus 6 amps, which I can add together to make 10 amps. So that means negative 2 volts divided by R. Sorry, why did I keep saying R? It should be 10 ohms. We have a value for that. My apologies. So let's see here. So that means V is going to be equal to 10 amps times 10 ohms divided by a factor of negative 2, which looks to me to be negative 50 volts. So if V is negative 50 volts, what's our current IX? Yes, sir. Yes. Okay, so let's talk about that real quick. Okay, because that's we're about to figure out what IX is. Okay, so IX expressed in terms of V is negative V over 10 ohms. And the reason for that is because we have decided that V has this polarity. So that's a fantastic question, and it's something that you guys are going to run into very often in your homework assignments, in class assignments, and even on your exams and things like that. The short answer is, as long as you're applying the Ohm's law relationships correctly, the signs will actually just work themselves out. If you're applying them incorrectly, you're going to get into the position of where you're like, okay, so if it's not the positive answer, it's probably the negative answer kind of thing. Okay. But if we had scratch this guy out and put plus Ix right here, when we substituted this relationship in, we would get literally the exact same results, right? It's all about observing that since the current is flowing into the negative polarity terminal, our Ohm's law relationship needs to have a negative sign associated with it. Okay. Positive polarity on bottom. Yeah, that's starting entirely from what Mr. Stubblefield suggested at the beginning. We assumed positive polarity was on bottom, and so that's why we went that way. If we had made the assumption that the positive polarity was on top, then it would be positive V over 10 ohms. Absolutely right. That's one of the things that students seem to get the most frustrated with in circuit analysis is there are too many times where you have the option of making an arbitrary decision and it might seem awkward in some way, shape, or form. So if we aren't explicitly told what the polarity of a voltage drop is, we have to assume it. If we aren't explicitly told what the direction of a current is, we have to assume it. As you'll see over these next several days, if we aren't explicitly told how to solve a particular circuit, we get to choose a method, whichever one we are most comfortable with. A lot of you guys seem to like direction and don't much care for the freedom that circuit analysis allows you to really tackle any circuit in any which way you see fit, as long as the rules you're applying are sound. So, all right, so from this, we get Ix to be negative 50 volts divided by 10 ohms, which comes out to be 5. All right. So we only have 25 minutes left of class for today because we got a 25-minute late start roughly because of the projector issues and all that kind of jazz. So I would like for us to put the mini lab off until probably the end of, let's say. Oh, it's scheduled for Wednesday? Okay, well then just in class assignment today. My apologies. I thought we had a mini lab today. I printed it out. But I can't read a calendar apparently. Well, that's wonderful. 25 minutes for the in-class assignment then. I am done talking today, but if anybody has any questions or anything, I'd be happy to answer. Yes, ma'am. Yes. The circuit tutoring on Monday and Wednesday afternoons, it's from 4:30 to 5:30 p.m. in Nefkin Hall, room 105. I have senior design today until 5 p.m. roughly, so I won't show up until about 5, but I believe there should be a representative from Eta Kappa Nu there until I get there.